I'll be talking about a very similar problem, but in my case, we have to do compression. So we can't just take the original source and translate it the best we can or reconstruct it the best we can. We have to discard information. This is the main difference. And okay, I will prevent it from sleeping. It should be okay. Okay. So, hi everyone. So this work is a joint work with Aaron Wagner from Cornell University and my supervisor Dennis Kuntus. So it's kind of a, let's say, a similar problem to what was presented, but here with images or other kind of sources. But now the key thing is we are looking at lossy compression. So the notion of lossy compression is that you take an original image or whatever data you have, and then you have to discard information. The goal is to reduce the file size. This is a stated goal. And so we have no choice, we have to discard information. And so what happens when you use traditional algorithms like JPEG, or here this BPG is a little bit more advanced, but kind of similar, is that if you discard too much information, if you compress your image too much, you get blurriness or artifacts. That's with traditional methods. And now what people did is they used ideas from generative modeling. For example, here they use generative adversarial networks to design a compression scheme that gives this amazingly looking image with all these great details. And there is no blurriness, no artifacts. But there is no free lunch. If you do this, then you actually have to add certain details or colors which are actually not present in the original image. And so we get this kind of trade-off. So the difference with the previous talk is maybe there's a minus sign somewhere, that accuracy, distortion. Yeah, diagonally refracted, yeah. That's it, yeah. Exactly. And so there's this kind of Pareto curve that we don't see here. And yes.
So you reduce the size for obvious reasons, but when you put back something there, isn't it increasing the size again?
Yeah, exactly. If you add, let's say that, okay, if you put back additional details, like I said, like additional details of the face here or colors, then it will increase the size for sure. But maybe this is actually much better in terms of visual quality, because maybe we do not want to have a blurry image. That's the thing.
No,
so.
I mean, then you could have used the original if you had to use the size. Right? So I don't understand what you gain by first reducing and then adding.
Yeah. So when I say, sorry. Yeah, I think the idea is as follows. There are certain file sizes for images that could never have been accessed before. Meaning we take our images, we compress them to a very, very low file size, and we get a horrible reconstructed image that was not acceptable for public use. But nowadays, with this method, we can compress to extremely small file sizes. And yes, we will add a little bit of detail, but very minor addition. And so now people accept these kind of images for let's say kind of commercial use with file sizes that were never accessible before, really, really small file sizes. They are now further from the original image. You have to add things that were not there. That's the problem where you lose. But the file size is amazing, and the visual quality is quite good. So it's about accessing really, really small file sizes. That's where you gain. If you stay close to the size of the original image, you don't gain much. That is actually very true.
So you mean it's still a lot smaller than the original image in terms of size?
Yeah, if you want to, you can get very small in terms of file size. That it depends on the trade-off. So if you accept to modify a lot of details of the face, for example, if you don't have a facial recognition software problem, so you accept to modify details of the face, then you can get very small file sizes. If you want to maintain very close correspondence with the original image, then I think you're very limited in terms of the file size. Yeah. So I just wanted to stress, because to compare to the previous talk, here we have to discard information. So that means that the closest image, reconstructed image from the only available information that we have, once we have discarded information, it might actually be this blurry image. So if you take a mean square error, so you take pixel by pixel from this with the original image, you compare each pixel, difference squared plus difference squared, etc. It might be that the image which will minimize the distance will actually be a blurry image, because of the fact that we can only construct it from a limited amount of information. We have discarded information, and so with that we're supposed to reconstruct, and maybe the best is actually a blurry image. And this is why we really have a trade-off in this case. That maybe it was debatable in the other talk, although I think you give very good arguments. But here we really don't have a choice. Sometimes the best reconstruction in terms of distortion or distance will be blurry. So if you add details to make it look good, you will lose in terms of distance to the source. You will get further away from the source for sure. So this is a kind of example or numerical, let's say, example. But here you have a measure of distortion or accuracy, kind of like negative accuracy here. So the lower the better. And here you have a measure of visual quality. Again, the lower the better. And you kind of see this kind of Pareto curve that is there. And now the difference with translation is going to be kind of shown in the next slide. So what people did is, because generative models worked very well, they said, if we're going to do a mathematical formalism of this trade-off, let's take ideas from generative modeling. And that's what they did. So maybe, okay. Anyway, so, okay. So it's this constraint number 2 here that is going to come from generative modeling, which is actually exactly like what you showed before. So a divergence between two distributions, and I will explain this in detail. And essentially, my talk is going to be about criticizing this choice of constraints in the context of compression, which is going to be very different from translation. So let's go over the setup. So we have a compressor and a decompressor. Think of JPEG. You have a JPEG that compresses the image into file size that you want. And then you have the decompressor, which just opens the file. Here in the notation, the number of bits, the number of zeros and ones is the exponent, nr. So the reason you have an n here is because in this talk, we're going to be talking about the compressibility of very large sequences of IID random variables. So the reason why we do that is first because this is like the seminal approach of Shannon, and that's something that is vastly studied, but also because we know that studying the IID case usually gives insights onto the general case. So for example, if you don't care about realism or visual quality, then it's been shown that actually studying the IID case gives you nearly the exact same result as studying the general case. Now, when you add the realism constraint here, this might not hold. You might not have a direct equivalence between IID case and general case, but I hope that we will get some insights, at least, about the general case. So xn here is a IID sequence. Oh yeah, it's a discrete sequence. So x to the exponent n just means a sequence of length n. That's all it's going to mean. And yn, again, is a sequence of length n, trying to reconstruct xn from limited information. And so as we saw in the previous talk, it's quite natural to have a notion of distortion with a kind of distance. So here, because it's sequences, you have an average over the position in the sequence. So you compare x1 and y1, then x2 and y2, etc. And as I said, we're going to be looking at very long sequences of ID variables. So this is why you have these kind of limits. So you care essentially about what happens when n is large. And so I think that to better understand constraint number 2, we should look at the case where this capital pi is 0. So as n grows larger and larger, the distributions are supposed to match. Which distribution? So delta is some divergence, measuring some kind of distance between distributions, where we have the source distribution, which is IIdPx, and then the reconstruction distribution, or you can think of the compressed image distribution. Okay, I'll be talking about total Fission distance more, but you can use any other kind of distance in our results. So now the question is this the right way to measure realism in the context of compression? Why? Because first of all, I don't know if you might have been familiar with this idea of having a small distance between distributions is something that is typical in generative modeling. We want essentially a generative model to be producing the same distribution. I mean, the generative samples or artificial samples should be essentially the same as the real or natural samples. And so this is quite typical, but then this means that what we're asking from our compression scheme now is that essentially the decoder should be a great generative model. You input bit strings into the decoder, and then the distribution that is outputted should be very, very close to the target distribution. And this is the first question. Do we really need, for an image compression algorithm, to essentially be a great generative model? Is this really what we need? Another way to say this is that I believe that requiring a vanishing divergence or a small divergence between these distributions does require realism, yes, but it requires, as I said, great generative model performance for the decoder. And it also, another way to say this, is that it's the ability to fool the best mathematical hypothesis test between these two distributions. So a test or critic which is supposed to decide whether a sample comes from either distribution. And we know that the best performance of said hypothesis test or critic is directly linked to the total Fission distance between the distributions. So minimizing that, meaning being able to fool the best possible mathematical critic. So when we know that what we care about is whether a human will find the image realistic or good looking, do we really need to be able to fool the best possible mathematical test? And I think in generative modeling, these questions might not be problematic, but in lossy compression, it's really key. What we are saying is that by using this constraint, we are adding unnecessary restrictions, unnecessary demands on our compression scheme. And in a compression scheme, the whole point is to reduce the file size, to compress. And so if we add additional restrictions that are not useful, we are going to require more bits, more information to be preserved in order to satisfy this. So we're going to be very suboptimal if we try to reach this very, very difficult goal, which we don't need to reach. So that's very specific to compression, where we need to optimize resources. And so essentially, my talk will be about to propose a new way of measuring realism. And hopefully then after, I will essentially be able to characterize information theoretically, the trade-off, like if you see, in some sense, the Pareto curve that you saw. And hopefully our approach will kind of give insight or give, let's say, evidence that this new constraint is going to be more suited than the divergence-based constraint in our specific context of lossy compression. So there will be a bit of suspense, like I will not give the new constraint right now because there are a lot of preliminaries, so I will slowly build up to that. And it will be quite informal for a few minutes, and then I will give the actual formal definition. So let's just start by just emphasizing that in lossy compression, you can get very suboptimal if you add unnecessary constraints. So this first or initial formalism that I showed with a divergence being small has been studied theoretically. So we know the Pareto curve with that constraint. And so we can say certain things. The big difference here with translation in the previous talk is that here we have two separate terminals. Meaning I can take a picture, compress it on my phone, but then someone else, maybe 1 year later, will open the file. So there are really two different locations, two different terminals, an encoder and a decoder. And the theory shows that if you impose this very strong constraint of distribution matching with a divergence, then you need common randomness between the encoder and the decoder to reach the optimal performance. So common randomness is a random variable that is available at both sides without the need for communication. It kind of comes from the environment. And the problem is that it's not just about getting a small number that is the same at both sides to agree on some way of compressing the image or sequence here. What has been shown in the theory is that just for the presence of this common randomness to be at least a little bit useful, at least to allow a 1% saving in compression rate or file size, you need the number of different values that the common randomness should take to be enormous. So RC should be at least 1% of the compression rate. So to give an example, if the compressed file is 10 kilobytes, which is kind of something that we encounter commonly for images that are compressed lossily, then you need the different number of different realizations of the common randomness variable to be at least to 800. So any implementation that you might try to do in Python or your favorite language will usually use a pseudorandom number generator that has a very small, a much smaller number of different values it can take. So we see a disconnect between theory and practice, where in practice, the state-of-the-art compression schemes, image compression schemes, are not using common randomness, and definitely not these large amounts of common randomness. And so, of course, the point is, if you don't have these insane amounts of common randomness, then you lose in terms of compression rate. You are suboptimal in terms of file size. Yeah.
Just trying to clarify like what the assumption is here. Here, this is a uniform path, right? So here, the encoder's coding distribution can be whatever.
Yeah.
But if you picked the coding distribution to be nice, then maybe reduce this. So think like, sorry, like it doesn't make sense to anyone, but if you're doing like the rejection counting, like type of realism should be coding to achieve this, then in the general case, yeah, you need exponential examples.
Yes.
So I thought of just now, like, if you picked the encoder to be subdithered uniform, one-tether, then maybe reduce this.
So okay. So I think that is like okay. So it's a very niche question, I think. But so the idea is, yeah, there are some distributions which optimize the rate distortion function, and these you have to stick to those. Okay. Long story short. But yeah, thank you for the.
Class over if you're optimizing, then maybe you can.
Yeah, you could actually.
Then you're not getting the rate distortion.
Oh, that's actually a good, interesting point. Yeah, if you really restrict your, yeah, you could get something different. Yeah.
Like my worries. Okay, maybe we can talk about.
Yeah.
Let's
For sure. So okay. So now, if it's not going to be like a notion of realism based on a divergence, what is the kind of best notion of realism? And so we're not going to be using the distribution of the reconstructions or distribution of the compressed images in some sense, but we're going to be using a score that will just take an image, think of an image, or here a sequence YN reconstruction, and give a real number. So it turns out that the question of how to measure realism has actually already been studied in algorithmic information theory for a long time. So this remark was found actually by Lucas Tais from Google, who noticed that the question, does a sample Y come from a target distribution P, is a question that's been extensively studied actually. And so now the answer to the question, what is actually realism or how to formalize it, is found in algorithmic information theory. And there is this kind of consensus, meaning that different scholars found equivalent definitions essentially, and they're all equivalent to this one. And so let's go over slowly. Let's go over this slowly. So the claim that I'm making here is that the notion of realism is encompassed by the values given by log-likelihood ratios. So log-likelihood ratios are going to give scores to a given image or to whatever sample you have. And if you look at all these scores, when you take into account all possible log-likelihood ratios and you look at the ensemble of scores, this is the best possible way to measure realism. Based on these scores, the analysis of these scores, we get whether an image is realistic or not, or whether a sample is realistic or not. So to just like clarify what this set is, it's a set of scoring functions. So you take here it's a sequence, well, it could be, let's say, an image. So you take something you want to test and you map it to a real number, a score. It's going to be a log-likelihood ratio where in the denominator you have your target distribution. So for us, as I said, we're targeting the source distribution, which is IIDP. That's our reference. That's what is a natural sample. And then in the numerator, you have some measure, Qn. And the constraint here is that Qn has a sum of weights, which is at most 1. So it's not necessarily a distribution. It could be slightly more general than a distribution. And it needs to have the same support as Pn. So now that I've kind of explained what the set is about, just to reiterate the claim. The notion of realism is encompassed by the values given by all these log-likelihood ratios. And if you know like hypothesis testing, you might see there is like this kind of direct connection where in hypothesis testing, like the kind of Neyman Pearson, like the best test is going to be in this form when we want to test whether the sample comes from Qn or Pn. And here what I'm saying is that we look at scores for many hypothesis tests where we try to see if the sample comes from Pn or something else, Qn, and then from Pn and another Qn, etc., etc. And the point is that like the algorithmic information theory literature has agreed that this is what kind of encompasses realism. And I think this will become a bit clearer when I will give kind of examples. So, okay, maybe I'll do this like that. Okay, so as I said, notion of realism is encompassed by these values, and we'll see how we can use them to make a more concise metric. And there actually, and this is one of the like biggest successes of algorithmic information theory, is that actually there exists one among these which is the best scoring function. Meaning there is one log-likelihood ratio that is the best at scoring realism, the most sensitive to realism among all those. I will make that more formal maybe in 5 minutes. And so I think this is kind of quite surprising that there is some choice of distribution Qn, which is the correct way of judging realism for a given sample. So to give you a bit of kind of intuition, let's kind of look at examples first, and then I will go to the actual formalism. So first, there is a restriction on the functions, on the log-likelihood ratios. They have to be computable, or actually lower semi-computable. But anyway, this constraint of computability is something that is when you work on theory and you produce results, is not a very difficult constraint for a mathematician, in the sense that there are tons of lemmas that will tell you how to decide whether a function is lower semi-computable or not. So you don't even need to actually know what it even means. It just applies some lemmas, and so you shouldn't be scared of this notion. And what is nice is that it includes anything that's going to be implemented in practice. In general, it's going to be computable. So what you can do with log-log ratios is actually pretty much anything you can think of. So for example, simple example, you have a sequence, as I said, yn, which you want to test. And now you're going to look at the frequency of a given symbol in that sequence. So first, Sx of yn is the number of occurrences of x. And now what I'm saying is that there exists a log-log ratio delta, which is going to be sensitive to the proportion or the frequency of x in the sequence yn. So delta is such that for any sequence of distributions of random variables yn, if the frequency of symbol x doesn't converge in some sense to what we would expect, which is a distribution the probability according to the source or target distribution, then the score of the critic or the likely log-log ratio delta will explode, essentially. It will not be bounded in its expectation. So we can test for the proportion or frequency of a symbol, or actually even a pattern. So you take a pattern of any length, and you can go and check the number of occurrences and the frequency, and compare it to the target frequency. What you can also do is something a bit more interesting, where actually you really care about the order of symbols in the sequence. So I will take symbols that are zeros and ones in my sequence yn. And so n1 of yn will be the length of the longest run of consecutive ones in yn. So you want to test whether yn is realistic by looking at the longest run of ones and seeing if it's too long or too short. And so there exists a log-log ratio that you can actually express such that for any sequence yn, if the number of the longest run of ones differs in an unbounded way from the expected number of longest run of ones, then essentially the score according to delta will explode again. So to give you an idea, just a second, actually the expected, what we would expect is a longest run of 1, which is log n, actually. That's what you can show this expectation is approximately. It's proportional to maybe the distribution precisely that the Q there. But anyway, it's a log n. So now, if you find a sequence which has log n number of like longest run of 1, or something greater than log n, like I don't know, square root n, then you know that this is not realistic. And sometimes professors like to give this like show off in front of students, and they ask students to like get random sequences from a coin, and then to actually try to write sequences on their own. And it's quite easy for the professor actually to tell that students usually don't write a very long run of ones. Well, actually, it should be at least log n in expectation. So anyway, so you can do pretty much anything you want with the log-log ratio. I think if you know the theory of hypothesis test, you know that you can literally do anything you want. You can do even more complex things, and I think this is important because this ties to the optimal critic or the optimal way of testing realism, and this is Kolmogorov complexity. So Kolmogorov complexity, it doesn't really matter what it is, but the idea is that it can spot any structure there is in your object. That's what it kind of is known for. It's not just about a frequency or a longest run of ones. It's anything you could find. And so if there is one metric which is going to be able to spot any inconsistency or any weird pattern that is not supposed to be there, is going to be essentially with Kolmogorov complexity. That's what algorithmic information theory produced. And if you're interested, like there is this great literature in algorithmic information theory about how Kolmogorov complexity is really able to extract any structure there is in some very formal sense. there is an optimality theorem that says that there is no better metric for certain tasks. So anyway, that was to give you an idea of about this formalism. And now, okay, so we know how to measure realism. We have a new formulation. And note that you don't need to look at the distribution of compressed images. You just take one compressed image, you give it to the test, and it will give you a score. So you can talk about the realism of a single sample. And so now we want to formulate a compression problem mathematically. And first, I just want to add that even the divergence-based formalism can be kind of done with a log-log ratio. When I say kind of, is that you need to give to this function delta, log-log ratio delta, an extremely large number of samples. And then you can build a delta that is essentially estimating the distribution PYN from the samples. I think it's quite simple. And then just plugging that in into a divergence. And so essentially this is a simple estimator of the divergence. So if you give enough samples, then you recover the previous formalism. And that's how we're going to compare our notion with the previous formalism. So now here's the slide where I give the actual new formalism that we propose. So first I said that we need a sample or many samples. What do I mean by samples? Let's be clear about this. What I mean by samples is you want to judge a compression scheme. You want to judge a software, essentially. You have an encoder and decoder. What you do is that you take some IID samples from the source distribution and you compress each one separately. So X1, the sequence number 1, gets encoded, then decompressed, and then you get Y1. And then completely independently, you just use your compression scheme again with X2, and you get Y2. And so this is what I would call getting samples from the compression scheme. So X1, Y1, X2, Y2, etc., or IID from this. And so again, we impose a level of distortion that can be chosen, this value delta, where you have exactly the same expression as before, except that now you have an average over the batch. So you have sequence X1, which will be compared to Y1, and then sequence X2 will be compressed to Y2, etc. So this is nothing new, really. The first constraint is nothing new. And now the second constraint is really what we propose. And that is, as you might have seen in the previous examples, all is good when the score doesn't explode for large n. And actually, this is exactly how it's theorized in algorithmic information theory, is that for larger and larger samples or sequences, we want the score to essentially be bounded, not to grow unboundedly. This is what they call realism. And so what we require is a strong constraint where we say, I want my compression scheme to be such that for every log-log ratio in the class, the score is unbounded. For a frequency test, longest run of ones, Kolmogorov complexity, whatever you want, for every delta in the class that I showed before, the class of log-log ratios, I want the score to be bounded. So it's a realism according to many, many different notions. And now this constraint, I will keep it on all the next slides so that you will have time to look at it if you want. And I'll give more comments about it as I go along. So first point, as I said, the consensus in algorithmic information theory is that the notion of realism is encompassed by the value that delta gives when delta spans this class of log-log ratios. So all these values are the ones which, let's say, the ensemble of values describes realism. The specific form, as I said, of bounded score is exactly what you find in literature. So as I said, you get typicality, which means the frequency is correct. When you satisfy this constraint, your sequences have the correct frequency. They have the correct longest run of ones. They have correct whatever you want to add. You can give a single sample and have a constraint defined for a single sample. But as you will see, hopefully, it's interesting to just make it more general, where we allow to have multiple samples given to this score. And so the notion of realism depends on how much samples you give. The more samples you give to inspect jointly, the more the critic has the opportunity to discover discrepancies between samples. So it's a bit tighter or tougher notion when you have more samples. And I think this will become clear in our coding theorems or results. So yeah, you want to go back to the slide? Yeah.
The batch size is the number of sequences like.
Oh yeah.
Because there's
Yeah.
the n v sub n.
Yes, yes. So as I said, since we're looking at the compressibility of long sequences, we're looking at sequences which are going to be very long, and n can evolve going to infinity if you want. And now, I personally would say just take one sample. I think it is the most like natural notion of realism is that you just have one sample and you can talk about its realism. You don't need more than one sample. Maybe if you really want, you can take 2 or 3 samples, but a bounded number that will not depend on n. That's what I think would be the correct.
It's unclear, like so if the batch size is 1,
Mm.
then these are still. Then you only have the y sub 1.
Yes.
If you have multiple batches, okay, so for each n, you can have a different.
Yeah, you can tweak. So if you want to get, I don't know, log n samples to give to your critic, so I don't argue in favor of this, but if you want your critic to really be good at to really be inspecting a very large batch of samples, I think it kind of makes sense to make it depend on the dimension. So for very tiny images, you might have a small number of samples. For very high resolution images, a lot more samples. I mean, you can take actually any sequence you want, but yeah, it's general, let's say. And so what we find, and this is our main result, is that if the number of samples that you give is not exponential in the length of the sequence, so this actually just means that Bn is not exponential in n, then you don't have all the need for extra resources that we saw with the divergence-based constraint, where we require the distribution to be close. I had shown in the previous slides that you actually need, between the encoder and the decoder, an insanely large amount of common randomness between the two. Very, very diverse common randomness. Here we say that deterministic codes are actually optimal. And so in particular, it holds when you just give one sample. And I just want to emphasize that we get away with, let's say, less resources, despite the fact that our realism constraint is quite stringent, because we're asking that for every possible log-log ratio, you have this score which is bounded, meaning for frequency, longest run of ones, whatever you can possibly imagine. And so despite this stringent constraint, we still get away with a minimal number of resources, essentially, minimal amount of resources. And this explains why in the state-of-the-art image compression algorithms, maybe this is why they don't actually use these extra resources that we talked about. So this is a possible explanation. And just to tie now everything together, we can have a general kind of theory of everything whereby we can actually recover the same thing as the divergence-based trade-off, where you ask the distributions to match, when you give an extremely large number of samples to the critic. So what happens in that case is that we recover exactly the same notion, actually, of realism. So our constraint is equivalent rigorously to that constraint. And then we get, of course, the same trade-off, the same extra resources that we need. And so to sum up, what I mean by this is the divergence-based constraint that I'm trying to criticize actually is equivalent to something like our constraint. So it does have the similarity that it takes into account all the log-log ratios which are relevant to randomness. All these critics or scores that encompass the notion of randomness, it takes it into account. But it does so when looking at an extremely large number of samples. So we find that the divergence-based constraint is actually requiring realism, yes, but requiring joint realism of a very large exponential number of samples. And this is essentially kind of the insight we get. So we want to say that therefore, it's not even a practical notion of measuring realism, in the sense that you need just an impractical number of samples just to be given to the metric that you're looking at. So that maybe is another way to see that it requires extra resources. It's imposing much more than the other notion. And so to sum up, our formalism kind of explains the gap between theory and practice, whereby we see that we don't need those extra resources. And again, realism is encompassed by this class of scores, which essentially is, in the end, have a rather simple form and have like a very fundamental in statistics, fundamental ties to hypothesis testing. And this is the going definition in algorithmic information theory. And so from that perspective, we don't need to have our compression scheme being a great generative model. We don't need it to be able to fool the best mathematical hypothesis tester. Maybe the important point we saw is that the notion of realism really depends on how many samples you look at. If you look at an extremely large number of samples, you're talking about a very different notion of realism. When you look at a single sample and you ask whether it's realistic, it's a completely different notion. Yeah, I think now I might actually pause to see if you have actually any questions on anything that I've said up to now. Yeah. Yeah. So there is a simple version of the question and maybe more deeper version. So simple version is to say that integral probability metrics, the standard one, like total relation distance is an example, what they're actually measuring is extremely fine details of discrepancy between two probability distributions. So essentially what we argue here essentially is that to spot these fine details that a total relation distance will spot, you need an enormous number of samples and you need to look at them jointly, meaning you need to look across the whole batch and maybe spot that maybe, I don't know, there is a certain pattern that is hidden somewhere in this large batch that is unrealistic. That will be spotted by a divergence. So divergence is really talking about the realism of a very large ensemble of samples. While if you look at a single sample and you look at our formalism, we can tell whether the sample is realistic on its own. You don't need to look at it jointly with other samples and try to detect very, let's say, high frequency patterns that might be hidden. But a divergence can spot those high frequency patterns. Now a bit more like deeper question is, okay, the integral probability metrics like total relation distance or whatever, actually in the formulation, as he showed, it depends on the function class. So if you have a large function class like Lipschitz functions, Lipschitz 1 or whatever, you have a very fine notion of how to distinguish between two distributions. But if you take a very small function class, it may be that it's a much weaker way of comparing two distributions. And in that case, I don't know how weak you can get actually. So it might be that you reduce your function class for your integral probability metric, and then you get something that's actually, let's say, a very coarse way of comparing distributions. And that might actually be related to what humans are actually doing when they look at an image and judge its realism. So the answer is kind of, I don't know. Integral probability metrics, I guess, are very vast. The most common ones are very stringent metrics. Like total relation distance, Wasserstein are really, really like fine-grained stuff. So I guess it's an open question. I think think you were talking about exploring this further, and I think it's a very good idea.
An interesting question. I mean, like I think maybe one very dumb thing as well. I mean, because if you have this universal log likelihood ratio,
Yeah.
critic, then if we were talking about it, that if you do this log likelihood ratio test between like the true distribution and use like the way you can set it up, the log likelihood ratio, the algorithmic information, use a Solomonov prior. Then if you take that as the log likelihood ratio and then you use that as the decision, then I think you can lose, maybe turn, to get back to divergence, maybe you can turn it into like some kind of total variation distance between the true distribution and maybe the normalized Solomonov prior, something like that. I'm not quite
I think it's a good time to talk about this Solomonov thing, it's actually
but we don't know.
Yeah, I think
yeah. So I just want to say, because some people might not be familiar, so the best test that I talked about, the one that is the most sensitive to realism according to algorithmic information theory, is something that will take this form. I think I'll start by talking about the form, and then maybe I'll talk about the rest of formalism. So maybe take this pointer. Okay, so so x here is going to be here any sequence of any length. What you do is that you're going to compute now the Kolmogorov complexity of x, meaning the essentially smallest compressed representation of x in some sense. And here, essentially, you put the target distribution. So it has a different notation because it's supposed to take a string of any length. So you can't just put PIID n, like n times p, because you don't know the length of x. So it's just a notation to talk about IID for any length of. But anyway, it's a target distribution here. And so this is like in a log-log ratio, this is in the denominator. That's why you have the minus sign. And in the numerator, you have something that is essentially 2 to the minus k of x. So with 2 to the minus k of x, you can form, in some sense, a distribution. Where the sum of 2 to the minus k of x is less than 1, actually, it's a known result. So you can form a kind of distribution. This is called the universal, actually semi-distribution, because it's not exactly sum into 1. But anyway, the universal distribution. And so, and it is very closely related to the Kolmogorov complexity. So this universal distribution, also called the Solomonov prior, as he was calling it, is essentially the prior that you use. I don't know if how well you know hypothesis testing, but the idea is that those local ratios are testing between two distributions. So in the denominator, you have your target distribution you want to test for, and the numerator, you have some other distribution. And what the result is saying is that the best way to judge realism is to compare the likelihood, according to the target distribution, the likelihood of your sample according to the target distribution, and the likelihood according to the Solomonov distribution, or the universal distribution, so-called universal distribution, which is essentially the idea that, so this distribution will essentially be like the distribution over naturally occurring objects in engineering. So the idea, the way I formulate it is like that. So if you have a very structured object, you say, okay, it might actually occur in some sphere of engineering somewhere, but it might be quite niche. I mean, the more complex it gets, the more niche it is. If it's completely random, a completely random object, then essentially the likelihood that it will appear in somewhere in engineering is very low. Like that someone will actually produce a seemingly completely unstructured object, where Kolmogorov complexity can spot no structure. There are some other details, like if you take small objects, these actually will just appear everywhere. Like simple objects just appear everywhere in engineering. That's normal to expect that. So, oops, sorry about that. So 2 to the minus k of x When k of x is small, 2 to the minus k of x is big. So for simple objects, it's normal to expect that they will occur with a high probability in the whole of engineering. While for very structured objects, you will get a smaller probability, but still like non-negligible. And for completely random objects, where the Kolmogorov complexity of the string is essentially like the string itself, like the length of the string, that binary representation of the string. So it's how you compress a string when you have no clue of any pattern. You don't see any patterns. You don't see any way to reduce the size. So you just go with just the simplest description of the string, which is the string itself. And then 2 to the minus k of x will be extremely small, and it will be very, very like negligible in some sense. So there's this idea that the best way of judging realism is comparing your target distribution, the likelihood under that, and then the likelihood under this universal distribution, so-called universal distribution, or Solonov distribution. Yes, that's yeah. I think maybe I'll, before talking about maybe the rest, I don't know if it's really relevant to the discussion. So maybe I'll just take some other questions if you want. Or actually, did I answer the question? I don't remember who was asking. Oh, you were commenting, and I was, yeah. Yeah. First I want to say something. So this is about measuring realism. So our contribution was to do that, to use that for lossy compression. So compression when you have to discard information. But you can use this for any application you want. In machine learning is not just about designing neural networks for compression. You have generative modeling, you have outlier detection, where this kind of stuff could be useful. So the idea now is that people we're just taking the idea from generative modeling and saying matching divergence is the natural idea, and they were taking that as formalism. But maybe for broader applications of machine learning where you need realism, maybe the true notion of realism of single sample might be actually the best thing to look at. In our case, it was the best thing to look at because we have to discard information. So we are resource constrained, very resource constrained. So we can't just go and require additional restrictions or additional demands that are not useful. Otherwise, we lose in terms of resources. And maybe in many other problems, you will have a similar thing where you really have to pinpoint what is realism and not be asking just more than that. I don't know if you have any question. Yeah. Okay. Not right now. Let me think. So yeah. It's a good question. Actually, a question. Do you think that when you put the average in the integral probability metric, oh, so you said it's still a metric, so it's a zero if and only if.
So there's like for IPMs, like there's some conditions on the function for it to be a metric.
Yeah, I see.
So you need some analogous notion of that for my stuff as well.
So I would expect that if you really have a metric, so you're trying really to match the distributions by taking the metric. I mean, yeah, I'm maybe going a bit quickly. Yeah. If the metric goes to 0, does it mean that the distribution essentially are eventually nearly the same? Not sure. Not sure, right?
The IPM doesn't matter what the function class is. It's always a semi-metric. So if the distributions are the same, then the metric will be 0. Yeah. And what you don't get is the other way around. If the metric is 0, then the distribution.
Okay, so what I was going to say is if you really are requiring the distributions to be really close, I think you will get essentially the same thing as here. You really need, this notion of distributions being close is about large numbers of samples. So distribution is described by a very large number of samples. It's enough to describe the distribution. So if we're talking about matching distribution, we're talking about looking at very large number of samples and all the intricate like correlations inside and patterns, etc. If it's very coarse notion where we don't really look at all the details, all the fine details, and it might actually look like what humans are doing. So yeah, I can't say yeah for now, but it looks like an interesting actually idea to the average instead of the soup. There any other questions? If not, then thank you very much for your attention.